Welcome back. We're looking at these examples of Gaussian processes, and we're building up a long list here, and we're going to have many more that we'll find also actually later on how to construct a huge array of different Gaussian processes. So the next one on our list was this Ornstein-Uhlenbeck thing, and these are two people's names, two physicists, if I'm not mistaken, and they defined a process with the following. Again, the mean function is 0 everywhere. And, oh, actually, let me use t. Usually it's thought of as over time. I'm using t when it's time and x and y when it's sort of space. The covariance function is now, it's very similar to this. Let me put exp minus alpha s minus t, but no square. And again, alpha is some positive number. So it's the same as this one, except it's not squared. And sometimes this is called the Laplace kernel. Sometimes this is called the Gaussian kernel, because it looks sort of like a Gaussian. But it's not actually, because it's not normalized. And so let's see what this does. Let's go back over to MATLAB and run this guy. So I think this one was, did I have this? Ornstein-Uhlenbeck. And indeed I do, and here it is. You just take the square root. So let's do that one. Run. What do we get? And it looks kind of like Brownian motion. In fact, this Ornstein-Uhlenbeck process was defined, the purpose of it, when they originally defined it, as far as I know, or what the history, the story is, that they defined it in order to model the velocity of a particle that is moving under Brownian motion. So this is a model, of a particle, the velocity of a particle moving under Brownian motion that is subject to friction. So, okay, so anyway, that's what it is. And it does this thing. So it's a little more spiky than the smooth one. Okay, that's Ornstein-Uhlenbeck. And now we get to some really, I think, some really sort of fun examples here. So these are cool. These show you the very broad applicability and flexibility of this approach. So here's a periodic Gaussian process. That's a periodic, not aperiodic. It's a Gaussian process that is periodic. So we're going to take s to be the real numbers. Our mean function, as before, is going to be 0 everywhere. And now our covariance function is going to be the following. E to the minus alpha sine beta pi x minus y, that quantity squared, the sine of that squared. And here, alpha and beta are some positive numbers. So that's the covariance function I'm going to use. And let's see what's going on here. Well, maybe, the sine, I won't decompose it and analyze it, but what the sine is going to do is it's going to introduce periodicity into this covariance function. And let's see what happens. So let's run it. I put that one in here with alpha equal to 1 and beta equal to 5. That's this particular kernel right here. It's number 5 on our list. Let's run it. And there it is. It's periodic. Isn't that cool? So cool. So cool. So this is actually, this is a random function here, and it's exactly periodic. Exactly periodic. If we were to draw, if we had like uncountably infinite computing power, and we could sample this at every single point on this interval from 0 to 1, then it would be exactly periodic. It would be exactly the same value at this distance of a period. So that's pretty cool. I think that one's neat. So this is due to, or at least I got it from somebody who attributed it to McKay, 1998, some publication in 1998. So that's neat. And of course, you can change the period if you want. And you can also, you could, rather than, if I didn't square that, then it would probably be something more spiky. So you can play around with all these different things. And by the way, actually, I haven't verified that one, I haven't personally verified that that is in fact a valid covariance function. But it's not giving us any errors, so it looks like it probably is. And here's one more fun one. This is a fun one. So I just wanted to, this is asymmetric, not, again, it's not asymmetric, it's a Gaussian process which is symmetric about the origin. And also I haven't verified actually that this gives us a valid covariance function, but so maybe I'll state that caveat. I just invented this covariance function, and actually let me put it on the next line, so because I'm going to run out of room. I just made this up to try to make it symmetric, and it works. It doesn't give us any errors, at least. So I can show you. What this does. One more parentheses. So this looks kind of similar to these other ones, to this square one, but instead of just taking the difference here, I'm taking the min of x minus, the distance from x minus y, the absolute value of x minus y and the absolute value of x plus y. And so you can think about why I chose this. I won't analyze it to try to explain the rationale, but you can think about maybe why I chose this covariance function, and with the idea of getting something which is symmetric. And let me show you what it does. So here I chose that alpha parameter to be 100, and this is min absolute value blah blah blah, just like I said. So let's run this guy here. Let's run that. Oh, and I need to adjust my, let's comment that, and we need to adjust this so we can actually see the symmetry. Okay, there it is. So this gives you a symmetric function in the sense that it's symmetric about the origin. It's a not a symmetric function in the algebraic sense. So every one of these samples is a draw from this Gaussian process, and they're all perfectly symmetric about the origin. Beautiful. So cool. That's neat. I could do this all day. Okay, so Gaussian processes are beautiful. I think we have established that fact. And oh, and one more really neat. Oh, actually, yeah. So here, let me show you this. I didn't show you this one before. So this squared exponential, I only showed you in the case of a one-dimensional, but we can also do a two-dimensional one of these. Well, we can do any dimension we want, but I have programmed a two-dimensional one, and it's easy to visualize. So let me show you that, because that's pretty neat. So I actually, well, okay, let me run it first, and then I'll explain the issue. So if I just run this using the same, so maybe let me show you the first one here. The one-dimensional, remember, was this 3, I think. It's 3. And it looked like this. Oh, shoot. I'm going negative. Oh, yeah, we can go negative. That's all right. So this was the 1D case. It was this nice, smooth, sort of bumpy thing. And now, in the two-dimensional case, you run this one. At the resolution that I'm using, it's not gonna give us something that looks very smooth. See, it's not very pretty. You can kind of see what's going on, but so I ran it at a higher resolution. I increased the resolution of this, and it took quite a long time. It nearly crashed my computer. It took like, I don't know, half an hour or something, but it worked. It finished the job, and here it is. I saved the figure so that you could see it. Rotate it around, so you get this beautiful, it's called the Gaussian random field. in the 2D case. That's just terminology. It's a Gaussian process with in 2 dimensions. And this is one sample from that Gaussian process with the squared exponential covariance function. Pretty neat, huh? It's cool. So the reason why people use these for regression is that oftentimes, like, you could actually, I mean, you could almost envision here, you can almost see it as, like, think of this, you know, like weather patterns. Like, let me put this down flat. You know, and you watch the news and you see the weather guy talking about the weather, and he's got, you know, this map of weather, and it kind of looks something like this. You know, you could imagine this almost like temperature or you know, some weather patterns. And so the idea of you know, why it sort of makes sense is that nearby points in this field, so maybe I'll just explain what's going on here. Each point, remember, each point in this plane, this is like x1 and x2, and each point x in that plane they're associated with that x, there's a random variable zx. And so for each x we get a zx, and all together, all of those zx's together define this random thing that we drew a sample from. And by choosing this particular covariance function, this one here actually, this squared exponential, by choosing that, we're saying that, because, so if you look at this, what's going on with this, points which are nearby, let's look back over here, points which are nearby have a small distance, right? And so e to minus that is going to be pretty large because alpha is positive. On the other hand, points which are far away, they have a large Euclidean distance from one another. And so e to minus that is going to be very, very small. And so their covariance is going to be large when they're nearby and very small when they're far away. And that is what you see going on here in this picture, is that points which are very nearby, x's which are very nearby to each other, like, you know, like this one here, and I can't point to one because they're so small. This one and this one are very nearby in space, and so their z values are also highly correlated. The covariance is very, very large relative to their variances. And so they show up very near to each other. When you draw a random sample, it's very smooth. It's this very smooth sort of shape, surface. And that's why this kind of makes sense for, especially for those kind of, you know, geostatistical applications like oceanography and meteorology and all that kind of stuff. Okay, so that concludes our, so we're back to the classroom now, and that concludes our nature walk of these different species of Gaussian processes. And next we'll take a little closer look at what a covariance function is and some of the interesting properties that covariance functions have.